Hi viewers, welcome to the channel FEA A to Z. Today we are in day 2 session. Let's see the content first. First we are going to see more about linear and non-linear analysis. Next we are going to discuss about numerical methods used in FEA. We will see one by one. To understand linear and non-linear analysis, first we should understand typical stress strain curve for ductile material. So this is a typical stress strain curve for ductile material. First we should understand the zone 0 to A. It is called the proportional limit. B point is called upper yield stress point, C is called lower yield stress point, D is ultimate stress point, and E is fracture point. So we can segregate this entire graph from 0 to E into two regions. First 0 to A, it is called elastic deformation zone, and A to E, it is called plastic deformation zone. So with this zone we can differentiate linear and non-linear analysis. So in this zone 0 to A, the geometry will undergo elastic deformation, so that if we remove load, applied load, it will regain its original position. So this is called elastic deformation zone. So if we are doing analysis in this zone, within this zone, it is called linear analysis. And the next zone is plastic deformation zone. So in this zone the geometry will undergo permanent deformation. So if we remove applied load, it will never regain its original position. So this is called permanent deformation or plastic deformation. If we are doing analysis in this zone, within this region means, then it is called non-linear analysis. So this is a clear view or a simple example to differentiate linear and non-linear analysis. So while coming to non-linear analysis, we need to consider three things. First one is material non-linearity. So in this elastic deformation zone, the stress will be directly proportional to strain. So it will obey Hooke's law. So beyond this zone, the stress will not be proportional to strain. So that material will never obey Hooke's law. So that we need to give material property input for ultimate stress point or yield stress point. Any of this stress point we need to give in material property. If we are considering this zone in material property while doing analysis, then it is called material non-linearity. So next one is geometry non-linearity. So let's see one simple example. This is a tensile test mild steel rod. So if we are giving 100 mm displacement at this end by fixing this end, so the geometry will undergo permanent deformation, so that the initial shape of the geometry totally changed. So this type of nonlinearity generally called as geometry nonlinearity. So if we found any analysis or geometry which will undergo a permanent deformation, so we need to consider a nonlinear geometry effect also. So third one is contact nonlinearity. Let's see one example. So this is hyperelastic or rubber material and rubber geometry, and this one is steel geometry. So while applying load on this end by fixing this end, so at 7 mm displacement, this rubber model will be in contact with this steel plate, so that that kind of analysis will be generally fall into contact type of nonlinearity. From here to here, the load deflection curve will be straight line. Beyond that, we cannot predict the stress strain proportionality. So let's see the animation one by one. This is a mild steel rod tensile test CAE simulation. So here we can see that from here to here, so there is a proportional limit between stress and strain. So this is linear zone. Beyond this, it is non-linear zone. So that this kind of analysis will fall under material based as well as geometry based non-linearity. So let's see another example. And in this simulation, we can consider material, geometry and contact based non-linearity. So here from up to 3 mm displacement, the rubber model will not be in contact with steel plate. So after 3 mm displacement, the rubber will be in contact with plate, so that there is no proportional limit between force and displacement. So there is, the curve is parabolic. So there is no proportional limit between force and displacement. So this kind of analysis will fall under geometry, material and context-based non-linearity. Next content is numerical methods used in FEA. Generally, we have number of numerical methods. I have listed out most commonly used and efficient methods here. So first one is finite element method. So this is most commonly used method, and we will see more detail about this method later. And this method is generally used for linear, non-linear buckling, thermal, dynamic and fatigue type of analysis. This one is boundary element method. Here the outer boundary of the geometry only been considered for discretization. So this is efficient method for acoustics and NVH kind of problems. Next one is finite volume method. Here unit volume is considered, and all the problems will be solved by using Navier-Stokes equations. So generally all kind of CFD, computational fluid dynamics problem, will be solved by using this finite volume method. Next one is finite difference method. So here we are using Taylor series to convert differential equation to algebraic equation. So that this method is used in thermal and CFD coupled type of problem along with boundary element method or finite volume method. These are the most commonly used method. Generally we have to keep in mind one thing, so which is finite difference method using partial differential equations to solve the problem, and the rest of the three method like finite element method, boundary element method and finite volume method using integral form of equation to solve the given problem. So this is the main difference between finite difference method and rest of the three methods. That's all about today content, and this is about day 3 content. So we are going to see these topics in day 3 content. So thank you viewers. I request your feedback and leave your comment in comment section. Thank you.